Hello, ladies and gentlemen. This is section 6 of the circles and systems unit. Wow. And we are going to wrap up on kind of an interesting note because the problems in this section are kind of a grab bag. They all have to do with coordinate geometry in as much as we have coordinates to work with. But we're going to use all kinds of stuff that we've already talked about this year to solve some of these problems. So some of our techniques will be from this chapter, but others will be from first try or last chapter, or just kind of all over the place with this. And I want to do these so that we can talk about how there's many different applications of coordinate geometry, and it's tied in so intrinsically with all the other areas of geometry. So when we look at a problem today, we might not automatically be going for something that we've done in this chapter, like the circle vertex equation or absolute value. We might go further back to answer that problem. So for the first one, it says find the area of the sector of the circle shown. So we did area of sectors in first try, and when we did area of sectors in first try, we needed to use the area formula for a circle. And that area formula would be pi r squared. But of course, in order to use pi r squared, we need to know the radius. And we don't know the radius of this circle right now, but we can find it because we can do the distance between P and Q to find our radius. So if we do the distance between P and Q, that would be 6, 8 and 3, 4. Then we've got the square root of x2 minus x1, 3 minus 6 squared, plus y2 minus y1, 4 minus 8 squared. And that's going to give us negative 3 squared is 9, plus 4 minus 8, that would be negative 4 squared is 16, gives us the square root of 9 plus 16, or the square root of 25, which of course is 5. So the radius is 5. Once we know the radius, we can say, all right, well, we know this sector angle, that central angle is 60 degrees, which means that this sector is going to be 60 out of the 360 degrees in a circle. Remember that? So if we say 60 over 360, that's going to tell us it's this piece of our circle times the whole area of the circle. So pi times 5 squared. And if we figure this out, we're going to be finding the area of the sector. So 60 over 360 is 1/6 times pi times 25. If we want to make that simple, we can call it 25 over 6 pi. And of course, you can change it into the nearest tenth if you'd like to, or you can leave it as the exact answer there. So that's the area of just this sector. We didn't need point A at all. That's just in there as a red herring. The next one has to do with triangles. So find the value of y in the following equilateral triangle. We have all the other stuff. We've got 0, 0, 6, 0, and then 3, y. We could do a whole bunch of algebraic manipulation with slope and all kinds of different things and altitude to figure out what this coordinate is. Or we can use what we know about equilateral triangles. And if you take an equilateral triangle and you draw a line halfway through it, you might remember this, we get a 30, 60, 90 triangle. And we know from way back when that 30, 60, 90 triangles have a particular ratio pattern to them, right? If we have a 30, 60, 90 triangle, we have x, 2x on the hypotenuse, and x root 3 on the other leg. So we can figure that out here, right? If this is 0 to 6 and C is parallel to, is on the same line as A here, which means this is 3, AC is 3, which means that this line right here is going to be 3 root 3, right? If my horizontal distance is 3, my vertical distance will be 3 root 3, which means that that coordinate point is 3, 3 root 3, since that's the distance that we're going upward, which then is y is equal to 3 root 3. All right, so once we know 30, 60, 90 triangles, we can sort of give ourselves a break from some of the altitude work we normally would have had to do with a triangle like that on the coordinate plane. Finally, we can just be asked a whole bunch of stuff in a verbal form, that means without a picture, for some of the things that we normally use pictures with. So we have a verbal description. The point 10, 6 is on a circle centered at 4, 3. Write an equation of the circle. And you remember that in order to write the equation, we need to know the radius of the circle. So the first thing we're going to do here is find the radius with the distance formula. So we've got x2 minus x1, 4 minus 10 squared, plus y2 minus y1, 3 minus 6 squared. That's going to give us 4 minus 10 is negative 6 squared is 36, plus 3 minus 6 is negative 3 squared is 9. That gives us the square root of 45, which we don't really know what the square root of 45 is. We could simplify it if we wanted to, but remember that we just need to know that it's the square root of 45 for the equation. The equation in vertex form is going to be the center. That would be our HK center, so that's going to be x minus 4 squared, x minus h squared, plus y minus 3 squared, y minus k squared, equals the radius squared. And so the square root of 45 squared is 45. Make sure that you're always using radius squared here. That's one of the things that I see us make mistakes on a lot, is we don't use the radius squared. All right, letter B says find the coordinates of the point on the circle directly opposite 10, 6. So let's give ourselves what that might mean. So if this is the circle, and here's point 10, 6, we want to find directly opposite, like if we draw a diameter through here, what are those coordinates? Okay, there are many ways to do this problem. There's lots of algebraic ways you can do this problem, but probably the easiest, simplest way to do this problem is literally just by counting. So if we just count and we say, all right, here's my original center point, and this center point is at 4, 3, as per letter A here, and I need to find the opposite. So I'm kind of drawing a bigger version of my circle here. So here's 10, 6. And if I were to think, all right, to go from 4 to 10, I went 4 to 10, that's 6. I also went up 3 to go from 3 to 6. So I kind of went up 3 and over 6 to get to the next point, right? Because from 4 to 10 horizontally is a movement of 6. And from 3 to 6 vertically is a movement of 3. So to get the other side of my circle, all I'm going to do is I'm just going to backtrack. I'm going to go down 3, and I'm going to go backwards 6. And I'm going to think about what this coordinate would be then. So this new coordinate is going to be 6 left of 4. So 4 minus 6 is negative 2. So it's going to be at negative 2. And it's going to be 3 below this point at 3. So that's going to be 0. So this coordinate of the circle then, because we're going from 4 to 10, so that's 6 this way, and then from 4 to 6 this way, that's negative 2. And then we're going from 6 down to 3, and 3 down to 0. Right, so the point directly opposite is negative 2, 0. And again, that's all there is to it. The next thing we want to do is same problem. I'm going to try and show both of them up here. Maybe not. That doesn't work too well. Find the distance between 12, 10 and the center of the circle. Right? Don't get distracted by the circle work we've already done. All it's asking for is the distance between 12, 10 and the point on the center, which is 4, 3. So we will say, all right, we'll make a new distance formula. x2 minus x1 squared. So that's going to be 4 minus 12 squared plus 3 minus 10 squared. 4 minus 12 is negative 8. Negative 8 squared is 64. 3 minus 10 squared is negative 7. Negative 7 squared is 49. And so we get the square root of 64 plus 49, which is the square root of 113. And that's all you do. This is the distance. All it wanted was the distance between 2 points. That's what we've got there. And then letter D, find the distance between 12, 10 and the circle. Now remember, if we've got our circle here, and the circle is centered at 4, 3, and we want to find, let's see, 12, 10 would be 4, 12 over here somewhere. And we want to find the distance between those 2 points. We could know that finding the distance between this point and the circle is only going to be this distance right here. Only to where it touches the circle at a perpendicular sort of angle here. And we could do a lot of math to figure out exactly how long that segment is, or we could do some simple subtraction, because we know that all the way through this is the square root of 113, right? From this point 12, 10 to the center is the square root of 113. We also know that the radius of the circle from up here, we calculated in section A, the radius of the circle is the square root of 45. So if I take the square root of 113, this whole thing, and subtract the square root of 45, I am going to get the distance from this far out point to the spot just where it touches the circle and doesn't go inside at all, which is what I'm looking for here in part D. And so if I change these into decimals, that's probably the easiest way to compare them. That's like 10.63 minus 6.71 gives me 3.92. And once again, that's all you have to do. So some of your homework problems for this section might be a little bit different than you're used to, because they might not exactly match the problems that we did in practice today, but they're going to be similar kinds of problems, and I think that you know enough now that you definitely will be able to complete those with no issues. Have a great day. This is the last section for for the Circles and Systems chapter. See ya.